In Chapter 8, we will discuss the development of the modern periodic table and periodicity. The modern periodic table was developed independently by Lothar Meyer and Dmitry Mendeleev. However, Mendeleev usually receives credit. On this table, you can see how the table was filled out and when, and you can see that the gray, green, and purplish colored elements were those known to Mendeleev and Meyer at the time. As we've stated previously, all elements in the same family have similar chemical properties. This is because all elements in the same family have the same ground state electron configuration of the outer shell. For example, the alkali metals all have a single s electron in their outer shell. All the alkaline earth metals have 2 electrons in their outer shell. Elements are also classified based on their position on the periodic table. The gray elements and the light green elements are all known as representative elements or as main group elements. The blue and yellow-green are the transition metals, and this green and kind of peach color are what are known as the inner transition metals, or the F block elements, also known as the lanthanides and the actinides. Now let's use this knowledge to answer the following question. An atom of a certain element has 15 electrons. Without consulting a periodic table, answer the following. First, we want to know what is the ground state electron configuration of the element, how should we classify the element, and is the element going to be diamagnetic or paramagnetic? Since we know that the element has 15 electrons, if we start with the Aufbau principle and build up the number of electrons, we'll be able to determine the electron configuration. From that electron configuration, we can see what are characteristics of that electron configuration. For example, if it ends in the main group or if it ends in the transition group. We can also take a look at the electron pairing in the outer shell in order to determine its magnetic properties. So using the Aufbau diagram, we see that the electron configuration is 1s2, 2s2, 2p6, 3s2, and 3p3. Because the p subshell is not completely filled, then we have to be in the main group elements, since the main group elements have s and p orbitals as their outermost filled orbitals. Then, according to Hund's rule, since the 3p electrons must be spread into each of the single p orbitals, the element must be paramagnetic because it has unpaired electrons. The electron configuration of the elements also explain their bonding characteristics. For example, in cations and anions, electrons are either lost or gained until they obtain the closest noble gas electron configuration. For example, sodium loses its outer 3s electron to get the noble gas neon configuration. Calcium loses 2 s electrons to become like argon. For our anions, fluorine will gain 1 p electron to be like neon, or oxygen will gain 2 p electrons to be like neon. This explains why the anions and the cations have the charges that they do. This explains that there's a periodic relationship to the monatomic cation and anion charges that we discussed when we talked about nomenclature. Remember, group 1 plus 1, group 2 plus 2. Group 7 minus 1, group 6 minus 2, group 5 minus 3. This is in order to achieve the noble gas electron configuration. Since all of those ions share the same electron configuration, we call this an isoelectronic series. For example, the sodium cation, the aluminum cation, the fluoride anion, the oxide anion, and neon are all isoelectronic because they have the same electron configuration. For transition metals, we remove electrons from the higher N level first. So for example, for the iron cation, we remove the two 4s electrons prior to removing the 3d electrons. So iron 2+ loses those 4s electrons, and the iron 3+, we lose the 4s electrons and 1d electron. This is because the greater the N level, the farther away the electrons are, and these are also our outer or valence electrons.